as you probably know, I'm going to talk about monad transformers today. It's kind of a follow-up talk from a meetup we had at Atlassian a couple months ago. Along the way, I show some examples of using monad transformers from some of StackMob's source code, as well as a couple open source projects we work on. One of those projects is Scaliak, which is a wrapper around the React Java client, using a lot of, it's a Scala wrapper, it uses a lot of Scala Z, and using monad transformers with that library can be useful. So some of those examples will come from there. Another one is Scalamachine, which is a port of Basho's web machine framework, which is a HTTP application framework, over to Scala. And both those projects you can find on the StackMob GitHub org, so github.com/StackMob. And if you want, I do have a bunch of code on this slide, so if you prefer sort of following along on your computer, you can grab the slides up there. It's just speakerdeck.com/u/jrwest/p/monad transformers. If you need the link, let me know. And then lastly, before we get started, just a little bit about me. So I'm a developer here at StackMob. I spend most of my time in Scala, a little bit in Erlang, a little bit in Ruby. My background is primarily Ruby and Erlang, and now Scala. I've been doing Scala for about a year now, actually. A year is this weekend at StackMob. So Scala is sort of somewhat new to me relative to some of the other languages I've worked with. So as I mentioned, back in May, there was a meetup. John from Atlassian gave a talk on the type classopedia, which is this awesome reference for functional programming that Atlassian hosts, and there's one for Haskell, but it's nice to have something for Scala because we don't always have good documentation for us, and you kind of have to go learn the Haskell syntax. So how many people were at that meetup? Okay, some of you guys. And the content itself, so some of the basic type classes, functor, applicative, monad. How many people here are decently familiar with that in their minds? Okay, so I have a little bit of review. I'll kind of go medium speed, and if you guys have any questions, feel free to just shout out and interrupt me anytime. So John talked a lot of things. One of them is he talked about this type class. I'm assuming everyone's kind of familiar with the type class pattern, right? Okay, so he talked about one of these type classes called the monad, and it extends this other type class called an applicative, so every monad is an applicative, and I'll kind of just hand wave over that for now. And more importantly, there's this method flatmap, which, and I've tried to sort of smooth it out in these slides, but it's sometimes called bind, it's sometimes sort of written as greater than equals, except for places where I actually have compiling code. I've tried to use flatmap everywhere. But so there's sort of this, really there's these three important methods that are going to be sort of key to the rest of this talk. So the first one is point, which comes from the implicative type class. And that essentially lets us lift a pure value into some monad or into some context. And then we have map from the functor type class, which lets us lift a pure function that operates on a type A and returns a type B, lift it into some context or into some monad. And then we have flatmap from the monad type class, which lets us chain these operations together where one may depend on the one previous. So everyone kind of good so far? Cool. So a couple quick examples. In Scala Z7, we have this nice way of sort of explicitly grabbing the type class instance for a monad and calling one of the functions on it. So this is an example of that. So we're talking about the option. The option is an instance of the monad type class. We're talking about option here, pointing the value 1 into it, or we can map over it. Here's bind, but same as flatmap. In Scala Z, they call it bind in the type class. And then there's syntactic sugar for flatmap. And this is kind of that syntactic sugar, although flatmap, to be honest, is defined in the standard library, but you can see point here, which comes from the Scala Z7 syntactic sort of extensions there. So we have more of the object-oriented looking feel to our code. And really, what I think was kind of the core sort of thing that leads to this talk is how John left his talk at the end. And he presented sort of one, and it's important, this is really only one possible intuition for monads, but he said that a monadic for comprehension is an embedded programming language with semantics defined by the monad. So when we're working in this for comprehension, we kind of have this little mini programming language that has these sort of semantics of depending on what our types are. And he sort of left it with showing one monad wrapping a value, like option or something like that, and mentioned that as we start to compose these or stack them, it gets much more interesting, and that's where monad transformers sort of comes from. So at the simplest level, right, we maybe have something like a value which may or may not exist. And really quick before I move forward, John had actually called option like anonymous exceptions. And so one thing I think that's important about monads is the semantics you have some choice over. I mean, the types do communicate something, but option can mean this value may not exist somewhere. It may mean I don't care about exceptions. You sort of, depending on your code, are sort of choosing those semantics to an extent. Another example is often debated in the Scala Z room is whether or not validation, similar to either, is a monad. In some people's mind, it's only an applicative because of its semantics, whereas at StackMob, we kind of tend to bend those semantics because we found that success and failure is easier to reason about than left and right, even after using it for a while. So it can be dangerous, but you also sort of have a choice. So anyways, so that optional value, we may need to perform some side effects to go get. Maybe it's a value that may or may not exist in the database, and we need to go out and communicate over TCP to talk to that database to get that value. And maybe along the way, there are some exceptions or something that may happen that we do care about that we don't want to be anonymous, or if I'm sort of choosing option to mean exist or not exist, that specific exception. These are all the other exceptions that may happen. And I've just chosen throwable kind of arbitrarily there. You can pick whatever you want as the error type. And then lastly, maybe we want logging in there also. So now we have kind of this big, beefy monad that at some point yields this value A when we get deep inside of it. But we've got a whole bunch of sort of composed effects there. So that's what we mean by stacking effects. But there's kind of a problem with doing this practically. So I can show you the types, but that doesn't mean you can work with them. And from a theoretical perspective, the reason is that monads do not compose. So to sort of fully understand that, we need to talk about composition and what compose means. And I'm going to do that kind of by example. So a type class that does compose are functors, and actually applicatives also. And so just a quick reminder of functors. This is the functor type class. We have this method map. As I said previously, it lifts this pure function into some context, lets us operate in that context. And what we want to do is we want to compose two of them. And in code, what that means is we want to write some function that, given any two functors, m and n, and in Scala we take those implicitly to say I want the instance of those two type classes, we need to define a new functor that is sort of this bigger functor where the map method operates on m, n, and a. Right? But we're still taking our pure function. And so we want to write this function, and if we can write this function, functors compose. And in fact, that function's really, really simple to implement. You map over the outer functor, map over the inner functor, and then apply the function to that inner value. So everybody, cool? All right, and so an example of how that works in practice, we can use that to write, if we have m and a after we've done composing things, we can take a third functor and compose that on top, and we can kind of keep going. But one thing that's nice about Scala Z is if you're just working with two functors and you want to compose them quickly, it gives you this map2 function that does that. So you can see an example here. I have this function, which I think it takes the length of a string. And I'm using that same function to map over an option and a list of options. Using map2, so I'm composing those two functors. And so, alternatively, what I would have been doing is mapping over the list and then mapping over the options or a for comprehension or something like that, which is just a little bit, it's the same thing, it's a little bit noisy, it's repetitive, right? That code is encoded in here calling map twice. So there's no reason to type it everywhere twice. So the problem, again, from a theoretical perspective, is monads don't compose. And what that means is we can't write this function, taking any two monads, give us this new, bigger monad. So if you try to implement this fat map method, you won't be able to get it to compile in any form. And really, I'd suggest trying it. You can go take it down. That's kind of where it clicked for me, is why I suggest it, is you're kind of like, I don't really get it. And then you go to type it, and you're like, oh, this is impossible. There's no way I can get to a compiling piece of code. There's no trick you can do, nothing. You're just screwed. And if you want to find out a little bit more about it, a lot of these slides are sort of examples taken from Tony Morris's blog. He has a blog post called Monads Do Not Compose, and there's a nice gist up there you can clone and actually try out. It's all compiling up to that method, so you can try to implement that method yourself. So that's great from a theory perspective. We here kind of are on the cusp of using functional programming a lot, but it's not necessarily the core. So for us, it's always about what practical benefits we can get. So I kind of want to talk about how this problem presents practically. And for me, it really results in nasty code, which I call stair-stepping. So to an example of that, or well, most people call, let's say we have a couple values here. Again, we want to get some data out of somewhere. That value may not exist. It takes some side effects to get. And on this myData fictional type, we have this merge method where we can put two of them together and magic happens. So we want to write some nice code that deals with that, and maybe we take a stab like this, right? The problem is data 1 and data 2 aren't my data, they're options, right? So we have IO here. When we strip it off, data 1 is an option, data 2 is an option. So that doesn't work. So maybe we try this. Don't do that. Calling unsafe perform IO like that is bad. So this is wrong. I mean, it functions, but it's wrong. Here are a couple other examples that also function that are just awful. This one has some nasty pattern matching. This one has nested for comprehensions, which really kind of gets loose. If you're familiar with some of the other type classes, you may notice that somewhat have a contrived example, and this is a semigroup, and you could basically make this a lot simpler. But let's say this was a little bit less of a contrived example. I tossed this in. Things just got more complex. So you're not saying bullshit right now. Here's an example from StackMob's code. Before I knew about monad transformers, this makes me want to cry. A couple reasons. A, it's just super hard to read. B, I'm sort of like folding down validations and then folding down options just to create the same validation out to deal with the error because I haven't dug into the monad properly. So we have a service called Barney. Actually, I guess we joked that at one point we're going to have to say Barney out in public. But yeah, so we have a service called Barney, and it throws exceptions called Barney exceptions. It doesn't throw them. Rather, we use the exception type as our error type, although we don't throw them. Instead of building custom error types for everything, we just use the throwable hierarchy. So that's a problem, but the whole point is to kind of figure out how to deal with these things. So there is a solution. And just to point out, this is a solution, not the solution. And we'll keep working with that IO option example, and we'll sort of build to monad transformers. And again, please feel free to stop me on the way. We're going to get kind of into heavy code at this point. So what we're going to do is, for the IO option, we're going to essentially make a new type that boxes that value. And I've chosen to do that with a case class for brevity, but you can do it however you want. It doesn't have to be a case class. But we box that value, and then what's important is this new type here, we can define an instance of the monad type class for. And so you can see for point, we essentially point the pure value into the option monad and then into the IO monad. For map, that essentially is that's our composed functor method, just less general. And flat map, we flat map over the outer IO, and then we essentially, based on if the option is a sum or a none, we apply the function or we don't. So with that implemented, we can take that first nasty example and we can actually write our nice for comprehension. And the reason is now our IO options are boxed by this new type. And the only real difference is down here at the end, when we want to get our value back, we have to access the run field. So that's how we get back our IO option. We unbox the value. Another quick example. How many people are familiar with the state monad? Okay, I'll do it quickly. Basically, the state monad gives you the ability, it gives you sort of the facade of a mutable state, or of mutable state in your programming language. It's actually, in fact, all immutable. But it sort of looks like an imperative programming language. You can say get and set and maybe plus equals and those kind of things. And so and it's essentially a two-tuple. And when you fix one of the values to a type, or when you fix one of the types of the two-tuple, you have a monad, and we call that the state monad. And so we can do the same thing if we have, instead of IO wrapping option, if we have my state wrapping option, we can box it in a value, and we can define the the instance of the type class again. What I've done is left them side by side. I'm not going to re-explain the implementation because they're the same. But if you can, I don't know if it's kind of hard to see, but the lighter yellow are the only differences in the implementation, are the types. So one takes in MyState and one takes IO. So that's an area where we can generalize. And that's how we get to monad transformers. So what we do is we pull that type constructor of a single type out into our new type definition. So now we're generalizing on that M that wraps option. Okay? And we haven't really said anything about M besides the type constructor of one type. So to restrict M to a functor and a monad in the appropriate places, well, I guess let me take a step back for a second. Instead of defining the type class instance the way I have been before, I'm going to define the map and flat map methods on this case class. This is how it's defined in Scala Z, and I think it makes it a little bit easier kind of once you get to this point. So we're doing the exact same thing. It just looks slightly different. And so the way we restrict, in this case, M to be a functor for map and monad is we take the implicit instance of the type class, just like we did in previous examples. And then we can implement those methods, right? And this looks pretty much exactly the same. We have the map method. This is the generalization, slightly less general than the second example, not as general as the first one I showed you. And then the flat map method looks pretty much the same also. And side by side, you can see we basically generalized it just wherever we had the specific type before, we're dealing with the general monad we may be working with. Everyone feeling good so far? All right, cool. Let's see how we doing on. OK. So a couple examples. This comes from Scalamachine. And in this case, this is determining if the E tags of a request match the E tag of a resource. A quick caveat, I think this code's a little bit old. It doesn't exactly match RFC 2616 right. It doesn't deal with doubly quoted strings, so don't go use this code in production, please. It won't work. But the important part are sort of the highlighted parts, the monad transformer parts. So you can see we have an optional value, an E tag that may or may not exist, and we lift that into our state monad, which I call flow state. Essentially, RecRef's data has state about the request and response, like headers and the request body and the response body. And then we wrap that all in option T. So the value E is a string out there. You can see in the comments where E is a string. And then in the next generator, we're looking for the if match header. So we're looking for the E tags that the client has sent down. And and that is from Scala Z, it's lenses and state, and we essentially get a state action back that returns an optional value, an optional string. An optional string, and we wrap that in option T. So matches is also a string, and then you can see we do some stuff with both those strings to figure out if the E tags match. And then at the bottom, this getter else is actually on option T, and I'll explain how we get that getter else here in a bit, but it's sort of got to maybe get you guys excited. You can see that we can sort of use the old interface that we're used to with monad transformers. So another example from some of the same code. Here we're talking about determining the content type of a request given that there is a content type header, I guess. So we're parsing some media types, and then we're taking the first one out. And again, we wrap those in option T, and out we get, we can work with those inner values in the yield. So that's a decently simple example. One last example, changing pace a little bit to sort of hammer home the adding effects to embedded languages. So John talked about lists being non-deterministic computation, right? So we don't know when this computation is going to complete. There may be more values that they kind of keep going. And what we may want we want to add some semantics that allow us to halt that given some condition at some point. And we can use either T for that, and you can use a couple other things also. This is an example from a Haskell article I saw. So if we walk through this list and we print the items out, you can see that even if items were just a simple list, this code really hasn't changed, right? So we haven't changed the semantics of the code at all. But what we can do now is we have this extra ability to halt by when we return a left, so the either T is right biased. So when we return a left, we don't continue down with the comprehension. So if we reach a number greater than 4, we stop. The string fail doesn't really matter. And if it's less than or equal to 4, we keep going. And we don't really care about that value that gets generated. And so what that does is it only prints 1, 2, 3, 4. So the second we get to 5, it stops. So we've added this ability to our language, our embedded language. All right, so enough of examples for a bit. Talk a little bit more generically about monad transformers. So we're going to talk about it in this fictional instance of, with this awfully named MyMonad, right? So we have some type. And so the naming convention for monad transformers, or at least what you'll find if you're using Scala Z, and from what I've found in Haskell, although I'm not admittedly very familiar, is it's essentially the name of the monad instance with a T tacked on at the end. So you have option T, validation T, either T, so on and so forth. And what that new type does is it boxes some value, which is that inner monad. Looks like I forgot a bracket there. Awesome. That inner monad wrapped with some M. The implementation restricts that M to actually be an instance of the monad type class. And the convention is to call that run in Scala Z 7 and 6. It sometimes switches between run and value depending on who wrote it. So run if you're using 7, and at this point, milestone 1 of Scala Z 7 was released, so everybody use it. Yeah, cool. So the other cool thing, and this is, I guess, sort of the point, right, is we're talking about stacking multiple of these, is that a monad transformer is also an instance of the monad type class, to be a little bit more accurate. But so that allows us to do some cool things, which we'll talk about in a moment. But quickly, we can show just the actual definition, right? And so we already had map and flat map defined on option T, so that's really easy to do. And point is the point from before. We point into option, and then we point into whatever the monad wrapping our option is. So if that's I/O, we point into I/O. If that's state, we point into state. And the last sort of cool general part about monad transformers, well, there are a couple other things that I've left off, but for what I'm going to talk about is that the monad transformer, the option T, the either T's, have an interface that's similar to the underlying monad. So option T has a similar interface to option, either T similar to either. And that's actually kind of something special to Scala because we sort of have this mixed OO-FP world. So it's one sort of convenience at the cost of you have way more type ceremony to do when you start doing this stuff, I guess. So here's an example of that. So on option T, we have get or else, which are very similar, except for or else takes another option T instead of an option. But get or else is pretty cool. You have M option A, and you can call get or else, and you have MA. So you're doing get or else working inside that monad. Which is nice, if you're doing I/O, so you're doing I/O lazily, you don't actually have to execute the I/O to work with that option. So with all that, we kind of get to the most important part, which is we can go more than 2 levels deep, right? So we've done I/O option, but that's really not all that practical. You're going to get much deeper sort of type signatures. And the reason we can do that is because since the transformer is the monad, the M that we're talking about is something we can wrap also, right? So we can keep going n levels deep, and it doesn't matter how deep we go. So quick, again, contrived example. So we have this validation T. So we have an I/O validation throwable A. We've wrapped that in a validation T. We've boxed it. And then we have this function do work, which I don't know why I left the parentheses on. That's not good. Anyways, that returns one of those. And in this bottom line here, we wrap that all in an option T. So if we were to map over that, we would actually be working on the inner int, right? So we could add 3 to it or something like that. So we've got option T wrapping validation T. Well, but it's not side effecting because the I/O is lazy. So it just returns the action itself. But I think that is what I was thinking in my head, yeah. And so here's an example of that from some of, we host some static files, and so we allow you to register, aliases, which are usually C names. I guess sometimes they're A records, but we call them C names. And in this case, I am fetching data out of Riak, so this is actually using Scaliak also. So I've got a reference to a bucket in Riak. Is everyone kind of familiar or know a little bit? It's just essentially a key value store, and it's in the Dynamo sort of style. And so you have these buckets where you can put in data, which is, I guess, not really equivalent to a database, but for the purposes of the discussion, fine. And so we're getting some values out of the bucket at some key, and that, it may throw exceptions and it may not exist, and we want to actually work it with that value, so we wrap that all in a transformer stack, and then we get that domain and we delete some keys. Although, actually, to be 100% honest, I'm not totally sure what this code does anymore. But I think it reads values and it's essentially part of our delete code, I believe, when we unregister. So you can kind of just keep on going, right? And that's what you want to do. Is I showed you now like a 3-level deep. You can go 4 levels deep. My first example also had the writer monad in there also, or you may have some state or something like that. So you can kind of keep going and build whatever you want. But one caveat is the order in which you stack monads matters. And basically by changing that order, in many cases, you're changing the semantics of your language. So an example of that is, say, the difference between option T wrapping my flow state or the state T, so state also has a monad transformer, wrapping an option. And it's a lot easier to see, actually, if you strip off the boxing value, right? So I have a state action that, when applied to some initial state, may return an optional value, may return a value. Or I have a state action which may or may not exist. The latter is probably not something that makes sense in most code. So the order of which the transform we use is important. You need to remember that when you're stacking things. In a couple cases, it doesn't matter. For the most part, though, always consider that. All right, so changing direction, sort of the last major topic of the talk tonight, is the MONADTRANS type class. So we have type classes. We can be happy with even more type classes. And the reason we have this type class is there's been something repetitive, which maybe you've picked up on in some of the examples, and we can remove that with a little bit more abstraction, and that's what this type class does. So here's some of that repetitive code, and what it is often we need to lift some values into our stack. So it may be partially lifted into our stack, but it may not be inside of, let's say, the validation monad yet. And we tend to have this pattern where we map over this inner part of our stack and point the value into a monad and then wrap it all. And we've done that a couple times. These are examples this is code from previous examples on my slides. And this is basically what we've kind of done, right? Is we have some MA and then we want MNA, so that's where the map and the point come in, and then we wrap all that in some transformer for N. And so we want to abstract that away. And the MONADTRANS type class, and specifically this liftM method, will do that for you. So the type signatures kind of get a little bit crazy here, but essentially we make an instance of the MONADTRANS for our transformer. So that type constructor there is for our MONAD transformer. So for option T or validation T fixed to an exception type, or either T fixed to a left type, we define it for that. And we're talking about essentially taking some GA, lifting it into that transformer. So we're going to lift it into the underlying monad, wrap it in a transformer. And so for option T, I've left out some of the definition because honestly the type lambdas will explode. You can't fit them on the slides. But this is basically the implementation of that method, right? So we have our map and we have our point. And then we wrap that all in an option T. And Scalamachine has this monad called res, which is similar to option, but it allows you to essentially halt the processing of a request and respond in either an error or a specific response code with a response body. And this is the implementation. Again, we have our map and we have our point. And then we wrap it all up. And when we're done, we get some nice syntax extensions from Scala Z when we import the monad syntax extensions that let us use it. So those are those 3 examples before. You can see A, they're shorter. B, what you're actually doing, right, is going to be on the left of the for comprehension. So you're kind of looking down the line. You can see what everything's doing. There's no noise on the side, so that's really nice. And that kind of results in this. So this is preparing some things from a response and checking the accept encoding of a HTTP request, and then either sort of continuing on with the flow based on the results or stopping. And we're using liftM here just to kind of clean things up. Beforehand, I put these on the slides before, and they literally just went way off. You couldn't get them to fit. So that's pretty much it. But so kind of in review, Stacking monads composes effects, right? So we're talking about this one intuition for monads that is an embedded programming language in our code. And when we stack these monads, our programming language gets more features or more effects that we can perform. But we can't compose any two monads M and N generically, and that poses a problem. So what we do is we pick one monad M, and then we say we can compose that with any other monad N. Right? So there was no other restrictions on M besides it was an instance of the monad type class. So it can be any other M that we choose. Not all make sense, obviously, right? And the order matters. But once we've done that, we can keep wrapping these transformers. We can stack them. We can build an N-level deep stack of transformers. Our language gets more features. And then we can use MONADTRANS, that type class, to sort of reduce some of the repetition that's involved with doing some of this code, right? Because we don't want really noisy code just for it to be pure. We have to write this stuff and read it on a daily basis. And then you'll have less nasty code because you won't STAIR-STEP, and that's always awesome. So thanks, guys. So thanks to StackMob and for you guys for coming out and listening to me blab for a while. Thanks to Marcana for hosting it and setting all that up. My buddy Kozmin, who so hopefully you guys found the slides and the font's kind of nice, and he set that all up for me. Before they looked really awful. And to the StackMob team for having to listen to this twice now. So thanks, everybody.